Hello, everyone. Today we're going on a journey here, and we're going to go through the process that I like to take when I have to port Yocto systems to Nerves. My name is Abelino Romo. I am a principal engineer at Redwire Labs. I help design and execute on the entire stack, from firmware on embedded Linux and microcontrollers, most likely Zephyr, to front-end, back-end, and also infrastructure. Also, anyone interested in Zephyr RTOS or bare metal Rust, feel free to pull me aside, and we can chat about that. So you want to create a nerve system. Where do you start? Let's talk a little bit about what nerves is. Let's just lay it all on the ground here, and you can think of nerves as having two major components here: a hardware-specific system produced by Builtroot, typically known as a nerve system, and then you also have a lot of Elixir tooling to help glue things together. And you'll use that tooling to glue the nerve system and marry it with your Elixir application to produce a FOP image that you can then flash onto your hardware. If you're also lucky, you'll be able to find existing Builtroot configuration under the Builtroot repository for existing hardware. But if it's very new hardware, you're probably going to be out of luck. And your best bet is reaching out to Yocto. Why Yocto? Yocto is the industry standard when it comes to developing board support packages for brand new hardware. Yocto is part of the Linux Foundation, and a lot because of that. It's also backed by many silicon and hardware vendors. And so when, for example, Compulab, TI, or any of the big hardware silicon vendors, when they release new hardware, they also release a board support package, a Yocto board support package alongside that new hardware. If you do see a hardware vendor release a Builtroot project for a certain project, I've often seen that those projects end up rotting because they end up putting their resources to maintain the Yocto equivalents, and they just leave the Builtroot project as more of a reference, and for people, if they really need Builtroot, to do the legwork and maintain it themselves. Now, we'll talk about Builtroot and how it's different and differs from Yocto. Both tools help with building custom embedded Linux systems, but both of them are very different in philosophies. Builtroot focuses on simplicity and ease of use, and will reuse a lot of the technology stack that most applications or most libraries end up using as their build system. So you'll typically see make files, kconfigs, and the tool of choice to actually build the entire Builtroot rootfs is good old make. Yocto, on the other hand, focuses on flexibility and scalability. So Yocto is more of an umbrella project. Everything in Yocto is its own repository. They call them layers. We'll get into the layer model in a bit. But everything in Yocto is layer, including its own core set of packages. However, Yocto does not Yocto does not refer to things that Builtroot refers as packages Yocto calls these things recipes. So anything that defines a set of instructions to build any piece of software library or binary CLI tool, that is referred to as a recipe in Yocto. The output of that recipe is what Yocto refers to as a package. So the nomenclature is definitely way different. And if you're thinking at the same time between both Builtroot and Yocto, it can get a little bit confusing. Sorry about that. So very much like for those that are familiar with Built-Root is a monolith project, and it contains a vast set of packages itself. You could think of that as the standard library of packages within Built-Root. Yocto has something similar, but it's in its own repository, and that in itself is a layer. And that is typically referred to as the Open Embedded Core layer, which contains the basic of packages to be able to build a minimal embedded Linux distribution. Now, Yocto recipes can use make, can use CMake, and similar tools to make those, to end up making or building, compiling those libraries or packages, but it itself does not rely on make to actually build a Linux distribution, similarly to how Built-Root does. Yocto instead relies on two tools, one called Repo, that is a Google tool, and the responsibility of Repo is basically to reach out to the entire plethora of repositories that could exist in the world and fetch all the repos, all the layers that you're going to care about for your project, and store them locally in a .repo directory. So repo uses a file called manifest, and that's where you end up declaring what are the repositories, what are the layers that you're going to care about in your Yocto project. So this manifest file is not specific to Yocto, it's specific to the tool repo. And the formatting is a very basic XML file that contains some metadata for defining where those repositories live and the names of the repositories that you're going to care for repo to pull for you and store locally. Now, the other tool that Yocto uses is called Bitbake, and that can be thought of as the build engine to build the entire embedded Linux distribution. And what Bitbake is going to do is find all the repositories that you've defined in your board support package or your Linux distribution definition, and attempt to build all those packages and combine it all to make a Linux distribution for you. So before we actually dig into the process of going from Yocto to Nerves, we'll want to learn a little bit more about a Yocto build support package project anatomy to better understand what are the bits and pieces in a Yocto board support package that we're going to end up caring about, so that we can dig into all those folders or files that we're going to care about to extract the information in order to compose a Built-Root configuration. So the most, I shouldn't say most, all board support package layers are referred to as meta layers in Yocto. And a meta layer has a very specific structure. There's a conf directory, which itself contains a single configuration file, and in that configuration file, we'll see global configuration for the board support package that project is trying to build for, and that could define versions of different packages. It could also define additional dependencies that the host requires. But it's global to the entire board support package, like anything that board support package might need to build successfully. And then we're going to have a subdirectory titled machine. And that contains machine-specific configuration. What we call in Nerves a hardware target, Yocto refers to that as a machine. So it analogous to a hardware target. And like I said, that's going to contain specific configuration for very specific hardware targets. And the other things that we'll be very curious about are two recipes. Recipes BSP, which stands for Board Support Package, that will usually contain anything regarding the bootloader. So we should see recipes in there for U-boot and any related recipe that the bootloader might require in order to actually boot the hardware. The other one that we'll care about is the kernel recipes. You'll see a bunch of recipes in there for both normal Linux and also real time, usually with Yocto board support packages. Now, we did talk a little bit about the manifest. That is not specific to Yocto. That is very much something that is brought in. It's a concept brought in from the repo tool. Meta layer, we just went through what an actual meta layer looks like. A layer that isn't a meta layer. So a layer is a set of recipes, so instructions to build some piece of software that are very similar. So you could have recipes for connectivity, which could define a bunch of recipes in there to build stuff for UDP, Ethernet, or anything related to connectivity. Could be modem, could be Ethernet, any sort of library for that. Any recipe that is similar should go in a single layer. And so, like, for example, here we do have recipes for connectivity. So you'll find anything related around connectivity under that directory. We also touched a little bit about on packages. It's not terribly important for what we're going to run through. The important thing here is the distinction between Yocto and built-root. It's a little important, just to not get confused. So hardware, for this conversation here, we'll be running through how to port the Compulab's IoT-GATE-IMX8PLUS from Compulab's own BSP meta layer into Nerves. And this is the exact process I actually took to bring Nerves to this hardware, which I hear some lucky people will win one or two of these devices. So stay tuned on that. First thing I like to do with any hardware that I'm vetting is download the stock image that that hardware vendor provides and flash it onto the hardware, because I want to make sure that I can flash something on it, not just whatever it comes with, and it's going to boot back up. It's going to work. This is also a good time to get to know the hardware, so experiment with it, list out all the peripherals and I/O that you might be interested in to make sure that it works. And also figure out how to flash it. So what utilities are you going to be needing, and what is the actual process for flashing? This hardware, Compulab, and anything around NXP, IMX core processors, they do use a utility called UUU, Universal Update Utility. That is pretty standard for the NXP family of processors. I won't get into actually using UUU. I just wanted to bring that up. That is definitely going to be a task for the audience here to figure out. What I don't do at that stage is do deep hardware validation. So make sure that all the peripherals work, mainly because I don't trust that image. It's just a quick step to figure out that I can actually boot, reflash and boot into the system that they provide, but I leave it at that. It's supposed to be like a 5 or 10 minute task. And then I move on to actually building the Yocto image, because I want to be able to reproduce what it is that they provide to create custom embedded Linux operating systems. And the reason for that is I just have trust issues. I don't trust that the image they provide actually contains everything that's in the Yocto layers. It could have more things, it could have less things. And more importantly, I have run into cases where I'm trying to compile the Yocto board support package for X hardware, and their main release or tip of main doesn't build. So if I can't build the Yocto system, how can I actually port it over to Built-Root or Nerves and make sure that it works then? I have to be able to build something and be able to reproduce it and trust that I can reproduce that. So first step is building that Yocto image. So I'll just go into the README, try to follow their instructions on how to actually compile the thing and actually try to produce an image. But with Yocto, one does not simply build a Yocto image. Why is that? Yocto, for each Yocto version that gets released, there is a validated set of operating system versions. So Ubuntu is definitely on the list of supported, and it often goes that they support all the way back to 18.04, which is great. We know that Ubuntu is supported, so you could spin up an Ubuntu VM. But I want to get this done quickly, so like maybe in 10, 15 minutes. So I just end up opening a terminal and running a Docker container. I don't typically set up a Docker file to try to reproduce this each time because this is really supposed to be quick and dirty. So I just start a container and provision the darn thing on the fly. And I don't list out all the system requirements. All that is very well documented under the Yocto system requirements page. So for the actual version that you're working with, definitely visit the docs for the system requirements. And then it's the basic setup stuff on the system, disabling dash, making sure that bash is the default shell, basic user setup, setting up locale, and configuring Git. And then I just take whatever I see in the README and try to build the actual image. So first of all is having repo fetch the manifest that we see in the README and overlaying Compulab's own manifest. They're using NXP's top layer manifest, which might contain the world of packages that NXP supports, and then they're just sprinkling on top. They're sprinkling on top a little bit of additional packages that Compulab owns and maintains. And we'll just use the repo tool. This is pretty basic when it comes to Yocto, and all this is actually documented in the Compulab's board support package README directory, which we'll look into a little bit later. We run repo sync, which is all it's going to do is collect all the layers that it found in the top layer manifest and in Compulab manifest, download all those layers locally into a .repo directory, and we just call bitbake afterwards to bake the image and produce something that we can flash onto the hardware. And this is critical, like as I mentioned earlier, because we want to be able to reliably reproduce and troubleshoot the image as we make progress on the Built-Root side. If we get stuck in the bootloader, it's probably because we did something wrong when we were porting the either package over to Built-Root, or we misconfigured something. But if it builds and runs from Yocto, you could port it to any other system that builds Linux distributions or embedded Linux systems. And at this point, since I can actually reproduce and create an image from a set of layers, this is a good time to actually take inventory of what's working on the hardware platform. On very, very new hardware, it's usually the case that not everything works, and that's fine. The team behind that product is probably going to be very busy fixing bugs the first few weeks, but our job is just to take inventory and figure out what is working and what's not working, so that by the time we get to a working Built-Root image, we're not surprised that something's not working in our nerve system. and we're not either confused about it. And yeah, like if it didn't work in the Yocto image, it's probably not going to work in the nerve system that we replicate. So that's okay. We at least can jot down what's working and what's not, and that way we're just not surprised later on. So at this point in time, we're gonna go scavenging. We're gonna go through the packages and layers that are of interest to us in order to be able to extract the information so that we can compose a built root configuration that we in Nerves land we typically refer to as a Nerves def config. So what are we interested in? We'll definitely want to figure out what bootloader they're using, what version, what repo, where it's being hosted. If they're doing anything interesting with U-boot environment scripts, we're probably not going to end up using anything that they have, but it's good practice at least to note that they might be doing something different. In the case that there might be some hardware quirks that we need to enable at this layer. Same goes for the Linux kernel. We'll want to figure out what repository they're using, where it's hosted, the version, the branch, and the def configs for both Linux and U-boot. And for firmware, if there's any special DDR firmware for training, any firmware for Wi-Fi or anything of the like, we'll want to note take note of if there's any special firmware mentioned throughout the board support package layers. So at a glance, if we dive into the BSP for the Compulab hardware, which is hosted under the Compulab GitHub org, we'll see at a glance that we definitely see a conf directory. That's great. We were expecting that being a meta BSP layer. We also see the BSP recipes, which we'll find bootloader stuff and anything around the bootloader in there. And we see the kernel recipe. And at the top level, those are the top three that we're gonna dive into. The other thing that we care about before actually getting into the files is figuring out where the top level Yocto manifest exists, what version it is, and the actual file. So from the README, if we format this line ever so nicely, we find the actual repository of the NXP manifests, and this is NXP's collection of actual manifest files. So all the manifests that NXP hardware vendor actually provides and maintains is going to be in this repository. This is also telling us that the branch we're interested in is the IMX Linux ScarthGap. ScarthGap, it is going to give us the hint of the version of Yocto this is using. This refers to, is the code name for Yocto version 5. And the file, the actual XML manifest file, we'll take a look at the actual guts of this a little later. But for now, we're just going to start taking notes of everything that we find for later. Yeah. So we'll just note what I just mentioned here under the Yocto table here. We haven't figured out everything else, so bunch of question marks for now. So in the top level configuration, we immediately see a layer conf, which is something that I mentioned earlier. This is the global configuration for this entire board support package, and it's just going to contain global information regarding the entire board support package. So let's dig into that one and see if there's anything interesting to note here. And the only thing that's interesting to note for us later is it does define a bunch of host tools. So these are probably going to be interesting. We won't note these in our notes. This is just telling us that it's going to require git LFS installed on the host system, bison, UU decode, and rsync. So if maybe something doesn't work down the line, it's probably because we had a missing dependency. So for now, we're not nearly close to actually getting started with the nerve system. We're just taking some notes here. So we'll just note those down for later and carry on. So we'll dive into the machine configuration. And we're adding support for the IoT Gate IMX8 Plus. That is the name of our machine. So we'll get into that file next and see if there's anything important there that we need to note. The first thing that we see is it's requiring an additional file. So it's importing something else. We'll dive into that one next. We don't know what's in there. But after that, we see that it's using a few device tree blobs here. So we'll definitely note those. Those are important. Those are probably going to come into play later when we start actually defining the Linux kernel. But for now, we'll note those, and it actually does say kernel device tree there, so very clear. It also tells us the name of the Linux kernel's config file. We're just going to note this. We don't know if this exists yet, but for now, we'll just add it to our notes table. And the other thing that we immediately see are the versions of U-boot and Linux. So for U-boot, they're on 2023.04 and Linux 6.6.23. So next thing is we'll get into that other file that got imported and see what's going on there. Oh, so this actually ends up complicating things a little bit. We see mentions of OPTI, SPL, ATF, all these acronyms that we really don't know what they are. I will get into a little bit of what those things are. OPTI and ATF are actually pretty cool technologies, but just know that this is going to complicate the bootloader process, porting the bootloader over to Nerves a little bit. But if we did dig in through the datasheet for the IMX8MP, we would end up finding out that ATF, the ARM trusted firmware, is a hard requirement for this platform. OPTI is optional, fully optional, but since the Yocto recipe defines it and uses it, we're also going to try to implement it. So ARM trusted firmware is mandatory because this line of SOCs implements something called Trust Zone. And Trust Zone is a hardware security feature that ends up splitting resources into two worlds: secure world, and normal world. And any resource that is defined in secure world, normal world cannot touch. So it's a really great way to split resources and isolate them from normal world into secure land. OPTI ends up adding a layer on top of that where you can run secure applications, which sounds pretty cool because then you can end up doing stuff around DRM for video or audio, stuff like that, or holding keys, secure keys in that area of the hardware that normal world can't access. You could request stuff through normal world, of course. You could talk to secure world, but it's really up to secure world to figure out if it wants to respond to you at all or simply ignore you. One cool thing about OPTI is I did mention that you can run secure applications on OPTI. Those applications can be written in Rust as well. So if there's any interest in Rust in the crowd, that's available, and that's an option instead of writing those applications in C, for example. And yeah, going down the same file, we still haven't finished this file. We do see also mentions of DDR firmware training. This is gonna be very important for the SPL layer. SPL stands for secondary program loader. This is a very trimmed down version of U-boot, and it's so trimmed down that it runs on SRAM. And remember, all these components have to run in Secure World. So Secure World itself has very limited resources. So the amount of SRAM that this has to run on is incredibly limited. So it has to be very, very tiny. We'll get into the responsibilities of SPL, ATF, and OPT a little bit later. But just know that SPL ends up loading the DDR training firmware, and that's going to be good to know later on in our process as we start porting some of this information into a build root configuration. Now, there's a little bit more metadata here. Some of this we don't really need, but it's good to jot down. A lot of these, like tload address, is very common and standard. And there's going to be a trick for this later on. But for now, we'll just note all these values and continue. The last thing we want to focus on this same file is this file ends up overwriting the upstream kernel and bootloader recipe. So if this board support package was using NXP's manifest, it would have theoretically used NXP's recipe to build Linux and to build U-boot. What this is saying is, hey, don't use the upstream recipes for these two recipe names, and instead use Linux Compulab and U-boot Compulab, which tells me that in this board support package, we should see a recipe with the name Linux Compulab and U-boot Compulab. And at the bottom, we do see that it also, we see configuration for DRAM. This might be important, maybe not, but we'll figure that out later. For now, we'll also note it. So now we have a bunch more notes here. We still have a few question marks, and a lot of that is still very much highlighted. And I left things highlighted because even though we have the information, we still haven't validated that these files, these things actually exist in their respective repositories. We'll get into diving deeper and figuring out if those things actually exist a little later. Now, first things up is the U-boot recipe. And I like to take a practical approach in what I'm interested in and what I dig into first. The first thing that typically boots in an embedded Linux operating system is the bootloader. So naturally, that's the first thing that I'm going to want to try to build so that I can flash that and see if the bootloader actually comes up on that hardware. So the first thing that I'm going to want to look into are the bootloader's recipes. So we do see two folders in here, one for MKImage. MKImage, we're not really going to get into, but just know that this is a tool used to merge SPL, ATF, OPT, and U-boot into one binary, which is going to be our final bootloader. We don't need to actually worry about it too much because built-root has a script that will do we'll use MKImage and package that for us later on. The same script exists in Yocto land. It's the exact same script. built-root copied it over to their project, and it's there for consumption on these sort of systems. On other platforms also, such as TI, TI also has SOCs that also implement Trust Zone. So they'll also use a variant of that script, and you'll typically find those scripts or a package that does the bundling of all those bootloader layers into a single final bootloader image. We'll also get into a little bit more of that later when I talk about ATF and OPT. So this is where flexibility ends up being a little confusing because in this layer, we end up seeing a bunch of symlinks. And these are the recipes. So a typical recipe has the file name convention of the recipe name, underscore, and the version of that recipe. So in our notes, we noted that the version for the bootloader is 2023-04, And the name of the recipe that we were going to want to look at was uboot Compulab. So this is the general structure for the file name for any recipe. And when BitBake comes along and traverses all these folders to find recipes, it's just going to try to follow the symlink and follow these files. If it's a real file, then it'll just open up the real file. If it's a symlink, it'll follow it. And all these symlink end up pointing to this file over here, uboot compulab main. And this is one of many strategies that you can use in Yocto land to try to dry some of this stuff up. But if you're not familiar with Yocto and how they do things, this might be a little confusing and hard to follow. So we're going to want to obviously try to open this file, which is going to open this. But we also see a bunch of includes that aren't symlinks. So my suspicion is this common recipe is going to end up requiring one of these things internally. And so we immediately see a require statement. So yeah, it's indeed requiring that include file, and PV stands for version. So the version of this uboot recipe, when BitBake actually expands its metadata, PV is going to be 2023-04. So if we go back to the previous one, it's going to end up trying to include this guy right here. So we'll get into the guts of that file because it's probably going to contain actual meaningful information for us. But the only other thing here to note is the name of the bootloader that we're going to end up naming in our build root def configuration. So this is something to note here. And I don't think there's anything else in that file. So moving on and looking at that other include file, that's where we actually find the bloody Git repository, including the branch that we're going to want to pull to build on, but it's not pinned to anything. So this is just the branch. This is supposed to have a git commit hash, but it doesn't. And that's one of those other things that is actually considered a best practice in Yocto, and having this as an auto incrementing rev, and that's what auto rev does. So if today the hash for this was A and tomorrow the hash is B, if you rebuild the system tomorrow, the hash, it's going to know that the hash changed, the git commit hash changed. So it's going to rebuild again. The problem with that is you don't have reproducibility in this sort of system. And the other thing that I don't like is if someone does end up committing something that is slightly broken, you're going to end up updating to that slightly broken branch or commit. So what I recommend doing is I do follow the branch, but I end up pinning in build root. I pin to the latest commit in that branch at that point in time when I set up the build system. And I like that practice because it's reproducible. And the other thing, there is no other thing. So let's continue. All right, so we have a bit more notes here. We do have, sorry about that. We do have a bunch more notes here for uboot. We noted the custom name. We noted the git ref, which is a branch. It's not an actual git commit hash. But we don't know, or at least we didn't see a def config file name for the bootloader. We saw one for Linux, but we didn't see anything for uboot. So, and this is where Yocto documentation might come into play. I have this knowledge from working on Yocto in 2014 years, and I know that if you end up not finding U-boot or Linux actually defining a def config, it actually ends up defaulting to the machine name underscore def config. And in this case, the machine name is IoT-GATE-IMX8PLUS. And coincidentally, that is the same def config that Linux ended up defining in its configuration. So maybe they missed that, but it's going to end up defaulting to this value. So I know I promised talking a little bit about SPL, ATF, and OPTI earlier. So let's take a look at some of that. At a glance, the important takeaway here is the boot sequence. Because we're going to want to go through that boot sequence successfully in order to boot into normal world. So we at least need to understand what the boot sequence is between all those different components. And troubleshooting them can be a little bit difficult, but theoretically, if you're able to reproduce what the board support package layer is doing, there shouldn't be any troubleshooting involved. And if you compile these things at the versions that they're specified in the board support package. Hopefully you don't have any problems. But anyways, it all starts with the boot ROM, and this is internal to the IMX8 SoC. This ends up it could initialize some hardware, but it doesn't really need to. The important thing for this component to do is to spin up or hand off to SPL, which is that very, very trimmed down version of U-boot, trimmed down enough to run on the secure portion of SRAM, which is very, very small. What this ends up doing is loading that DDR firmware. It could do other power initialization. What happens here isn't terribly important because once we get to ATF, the ARM trusted firmware, this has the utmost privilege in the entire SoC. So this can actually undo anything that SPL and boot ROM did and configure whatever these guys configured, however ATF wants to configure it, because it has the most top level privilege. Some of the responsibilities for ATF is set up power management, any other boot firmware that it might require for the entire system to come up properly, or I think for now that's good enough, but the other important thing is to hand off to OPTI, or at least start it. I know earlier I mentioned that ATF is mandatory for the IMX8 SoC platform, and that is yes, because we are in secure world. We need some firmware to set up secure world and eventually hand off to normal world. So what ARM trusted firmware ends up doing is it starts OPTI. It could also skip OPTI and go directly to our bootloader, because OPTI, like I said earlier, is completely optional. But in our configuration, we're going to want to configure OPTI, and all OPTI is doing is setting up a secure operating system where you can run secure applications on there. We're not going to have anything running on there, so it's not going to be doing anything. It's just going to be maybe a shell or a foundation for others to actually add their own applications on top of it. But in general, it'll be there for if anyone wants to actually use it. After this is done loading, ATF will actually eventually hand off to the bootloader, and all these just refer to the bootload stages. So boot ROM is bootloader stage 1, stage 2, stage 3.1, 3.2, and off to normal world is 3.3. And these are actually part of the specification. So if you guys get into the actual nitty-gritty details on ATF and the ARM spec around secure trust zone, you'll see mentions of these stages. Once we're off into normal world, the normal or the full U-boot bootloader ends up running, which ends up starting our Linux kernel. Now, in the previous slide, I did mention all these components that, for example, all of these SPL, ATF, OPTI, and U-boot, they all seem like different components, right? But to the hardware, all this has to be packaged up, padded, and packaged up at very specific offsets. So they have to be installed and flashed on the eMMC or the SD card in a very specific order and at very specific offsets, which is very brittle and error prone. But we're going to end up relying on MK image to do all that work for us. So it's just going to take all these layers, we're going to shove them through MK image through a script, and it's going to produce our final bootloader image that is just a single binary blob, and we can flash it using NXP's utility. Now, at this point, we actually talked through what ATF and OPTI is, but we actually haven't gone through the recipes. One thing that we didn't notice is in the area of the recipes where the board support package for this hardware, it was overwriting the recipe for the Linux kernel and U-boot. We didn't see anything overwriting ATF and OPTI. Which means we're not going to find these recipes in this board support package, Compulab's board support package. So we have to go through the manifest to figure out what layer in that manifest actually defines these recipes to get the GitHub repository URLs and the versions that these are defined in that layer. So to do that, we did take some notes on the actual repository name, the branch, and the manifest file. So we'll want to go over to the IMX manifest repository, switch over to this branch, and try to look for the 6.6.23.2.0.0 XML file. I know that was a mouthful, but going to that repository and switching over to that branch, we do see that that file is here. So we'll just dig into that file and take a look and see if we can pinpoint a recipe where we might think that layer might exist. You might need to go through a few of them in order to figure out or actually pinpoint the actual recipe, but it's the same process going down the stack of those layers. So while we're in here, I did trim it so that it actually fits in the screen here. We do see that there is a Meta IMX project defined. The repo is IMX. The reference for that should be, here it is. So this is the GitHub repository or organization, I should say, that we're gonna want to visit. The repo name is Meta IMX, and we should see something about ATF or at least BSP in that meta layer. So I know I didn't mention this earlier, but it's maybe a good time to mention it now. The value prop for layers. Layers end up removing, at least in the Yocto space, removing all the legwork that you have to do that you would have had to have done in built-root to bring all this information into a unified built-root configuration. So if NXP, for example, defines its layer for all of its SOCs, you just have to bring in that layer into your Yocto project and not have to worry about the Linux kernel, not have to worry about the bootloader, because everything's defined in that layer. And NXP, the actual manufacturer of that silicon, knows what they're doing when it comes to that silicon. It's their silicon. So they are a good authority to deliver and provide those layers. So now it removes, like I said, the legwork and the time that you would have put into figuring all this out. And all you have to do at that point is add your application layer below that. much easier to do. It's probably just building a single Elixir application, or in the case of other teams where you guys might be using C++ or Rust, for example, to build your firmware application. It's just a much simpler recipe to build that single thing, slot it in underneath your board support package layer that you don't have to worry about, and now that could produce a Linux embedded Linux distribution for you. So that is the value prop from for layers in Yocto space, but I won't go on that tangent further because then I'll lose my spot here. Anyways, we were trying to find ATF, right? So we immediately see a BSP package or layer, I should say here. We don't see anything else that's interesting. So BSP, we know, stands for, or at least we should see anything regarding bootloaders in there. ATF has a relationship to the bootloader, we know. So let's dig into that one and see what's going on. We immediately see the recipes BSP, which is something that we were familiar with. We should see some stuff about bootloaders in there. Let's take a look. And we do find the IMX ATF recipe in there. This one hopefully should be a little bit easier to extract info for. Maybe we don't need to extract a whole lot. And yeah, we immediately see the actual repo URL, the branch, and this time it's actually pinned to a git commit hash. If you dig into the actual repository, you'll notice that that git commit hash actually points to a git tag. So this is going to be good to note, and we'll probably want to use the git tag when we're setting up our build root configuration. All right, so we'll note that in our table. If you follow the exact same process, you can get the same information for Opti. For the sake of time, I'm not going to go through that flow, but just know, interesting note is they're both using the same git tag. All right, so we're actually done with everything that has to do with the bootloader. So the next thing is the Linux recipe. We see a similar pattern here where they're defining a bunch of symlinks. It's probably going to point to a .main thing. We see that there. We'll want to look at that first, but we know that ultimately we're going to end up in one of these include files based on the previous pattern that we saw for the bootloader. So in the Linux recipe, immediately we see something actually interesting. It's overwriting the def config that it had previously told us it was going to use. So now it's telling us, okay, never mind. The actual def config that you're going to want to use is Compulab V8 def config. We'll note this, and later on we'll actually dive into the Linux files, the Linux repo, and see if this actually exists. And as we surmised earlier, it is going to require that other file, so we'll get into that one next, and that's probably going to have the actual repository and the GitHub branch. And sure enough, it does. Under the Compulab organization, we'll want to dig into the Linux Compulab repo, and under this branch. Again, they're using autorev. I simply don't like that. What we'll end up doing is we'll just get the tip of this branch and copy that git commit hash and pin that in our built root def config. So now that we've actually finished collecting the information that we care about for Linux, let's dig into the Linux repository and just quickly make sure that the device tree sources exist based on the notes that we took, and also that def config, the Compulab V8 def config file. And those files live in very standard directories. So we'll dig into the Arch folder, and the architecture for this hardware is ARM64. So we'll dig further into the ARM64 folder there, and there should we should find two folders in here, configs and DTS, device tree sources. And that's where we'll be able to find the stuff that we're actually looking for. So we do see that a Compulab v8 def config exists. We'll want to copy this later into our Nerves project, but we can do that later. At this point, I just want to confirm that those files actually exist, and I don't have to figure out where they actually live. And as for the device trees, we also see that they exist in their respective in the proper directory. We see all three that we previously noted in our notes. So now we can actually check off all these things in our notes that we validated actually exist in the repository. So we don't have to worry about that. We know we're gonna want to copy the def config later, but that's about it at this point. And I think we have all of our notes. We don't have any more question marks. I left some of these highlighted, and that's just because for some of this stuff, we don't know for sure if it actually exists. But in terms of what we actually need to start composing the built root def config for our nerve system, this is pretty much all the information that we're gonna need. So the next thing that I like to do is I like to set up a bare nerve system project. And this could look something like this, just a few files. Typically nerve systems will have way more than this, but I end up adding as I make progress in the build process. So my built root def config, typically known as a nerves def config in a nerve system, I like to start very bare, very simple, just the tool chain and a few other things that I know I'm gonna need. And I start adding things as I'm making progress with the compilation process. And it all starts with the bootloader. So I know earlier I said SPL is going to require the firmware. So the order of bringing stuff into the Nerves def config is going to be, we're going to want to figure out how to bring in the firmware first, then ATF, Opti, then after that, then the bootloader, and then finally Linux along with the rest of the file system. So this is something that I ended up learning on the NXP platform because this is not the first NXP system that I bring up. If you didn't know this, you probably would have created a package that downloaded the firmware training binaries and installed them in a very specific location for later to actually flash onto the system. But there's actually a package in built-root, the Freescale IMX package, that contains all that for us. Like we just have to tell it our platform, which is IMX8MP, and it's going to download the training binaries and it's going to install them in the correct location. And this, because of that, you don't know what actually exists sometimes in built-root. So it's a good idea to dig into the packages that are available in built-root because there might already exist something that accomplishes what you need. This is one of those cases. Now, at this point, we're just plugging in all the notes that we've gathered from the start into built-root, and you could do this through menu config or directly into the def config. There might be a little bit of scripting later on to resource this basically so that mix compile, for example, so that it can take the new changes that you make directly to the file into consideration. So we'll just bring in the information that we have in our notes and bring in the custom tarball. We know from the notes that the platform name was IMX8MP, and we know that we're going to want to enable Opti. So if you go through menu config, you'll see a bunch of these options, and you'll want to play with these depending on the platform and depending on what it is that you're bringing in. We know that we want Opti, so that's the reason why we end up checking it here. Similar for OptiOS, we bring in the repo name, all the values that we gathered from our notes, and pinning it actually to the tag. If you're not familiar with the format, it's a good idea to take a look at other packages, which will use either the full URL expanded or these sort of macro function helpers. There is no one way to do it in Bloatroot, and oftentimes, if you talk to the maintainers, they will recommend one maintainer will recommend one form of doing this, which is might be like the full URL, and other maintainers will recommend this format. And lastly, we bring in U-boot. Now with U-boot, things are a little bit more complicated because we do need to enable a bunch of flags, but it's flags that we know we're going to need because we know that we're going to require a SPL U-boot. So we have to, oops, sorry. We have to check that flag in menu config, and same thing for the other sections of the bootloader, such as ATF and opti. And the rest of the stuff is pretty standard. If you take a look at any other nerve system, they might have very similar shape and configurations. So it's not out of the ordinary. We will, though, use the custom name that we noted early in our notes, because that is the name that the Yocto board support package was using. So at this point, we need to copy over some files. So we copy over the U-boot def config that we saw earlier in the, actually we didn't see, but this is a good point to get into the U-boot repository and validate that that file actually exists. And if it does, we'll want to copy it over. And I typically like to create a U-boot folder, and that's where I'll have my def config for U-boot, along with any patches that might be required when building the bootloader. So at this point, I think it's time to try to build U-boot. And we're not going to have a good time. We end up getting into compilation issues on this branch. I think these are solved on latest. I do have a PR up to bring this system up to date, which gets rid of these patches. But at this point in Git history, there are missing headers. Includes in some C files. So the patch for this might be kind of simple. You just got to dig through and figure out what are the actual includes that these C sources are missing, and put them in and create a patch for all of them. And as you can see, there were quite a few C source files that had missing includes. Like I said, I don't know how some of this stuff, oops, sorry about that. Some of this stuff ends up getting into main, but the main can be broken, such as this, for example. Now, if after the patch, we end up running into another issue, we're missing a system dependency. So you can solve this problem by either installing UU decode locally on the system that is building the build root image, or set up a package that brings in this dependency as a build root package, and have build root make that available for the entire build stack here. And that's what I opted for this system. The project that has that tool is called SharUtils. I won't go into the actual details of what the make file for this package looks like, but we do have a repository, like I said earlier, for this entire system, so you guys can dig into that repository and take a look at that package. So SharUtils is going to give us UU decode, and at that point, we should be able to get past that hurdle. And it's alive. Like if we build and flash the bootloader, we'll actually, we'll actually get into the bootloader. We see that we get past BL31, ATF, and into normal world U-boot. And we get into some environment error here. And this is actually a known issue. We knew we were going to get into some problems because we haven't developed the rest of the system. We're still missing U-boot environment. We're still missing bringing in the Linux kernel, and also rootfs. So next thing, logically is to bring in our def config and also the U-boot configuration, anything that we might need to set up a U-boot environment. And you'll typically need a few things in U-boot configuration: the size of U-boot env and the offset in Flash of where that should be flashed to. These are arbitrary. As long as it doesn't step over the bootloader itself, you should be fine, but you can pick any size that fits your needs and also the offset that you like. The one thing that we do have to tell the bootloader is what eMMC device this should go on, because sometimes they have multiple eMMC devices. In this case, we're going to tell it to put it on expect to see U-boot env in MMC device 2. And I know I'm running way over time here. Sorry about that. And so we enabled U-boot env in the bootloader's def config. We have to now enable the build process that ends up building U-boot environment, that U-boot environment binary. So we have to bring in host U-boot tools, and this is pretty standard. So if you take a look at other Nerve systems, you'll find that this is quite common in the rest of the systems. This package builds the U-boot environment binary and stores it in the binaries directory for the rest of the Nerves scripts to end up utilizing later to create our Nerves image. And we can't build a FWUP image to test at this point unless we start to bring in FWUP, rootfs, and a bunch of other dependencies. So at this point in time is where I take the time to bring in the rest of the world when it comes to Nerves and the configuration to properly make a FWUP image. And this might look very familiar if you guys have ever looked at other Nerve systems. We'll want to bring in FWUP, we'll want to bring in rootfs configurations, and any scripts that need to run after the fact that the Nerves tooling expects to exist in our Nerve system in order to create that final image. So we'll bring in our FWUP configuration file. The only thing that I want to test right now is U-boot env. So that's the first thing that the only file resource actually that I'm going to have in that file. Any other file resource you can either comment out or delete at this point in time, because we just want to make sure that U-boot env is flashed correctly and the bootloader actually sees it. And as I mentioned earlier, we'll want to bring in all the stuff around rootfs, including rootfs overlay. So that includes the Etsy directory with additional configuration and some post scripts here. Now that we have the basics to create an image, the easiest way to create a Nerves image is by creating an Elixir project using the mix tooling, such as a task mix Nerves new. We'll add our system dependency, which is just a local path dependency, and try to build the image. And next thing we'll want to do is flash that. And we'll also run into another problem here, but this one's different. It's not about validating the environment anymore. It's slightly different, but it read something, but it's off by, I don't know. It says that it exceeds the size, and it just failed reading it. This issue was a little bit difficult to troubleshoot. To troubleshoot this, you might need to either dump the flash from eMMC and compare it to the actual binary that you're trying to flash and make sure that it actually matches and aligns. Alternatively, you might need to actually troubleshoot the bootloader code, which is much difficult to do. And in this case, it was the latter. So the problem here was that Compulab's U-boot was redefining a weak function and doing some other behavior for that function. We end up want the original functionality. So to get the original functionality from that weak C function, we just go ahead and delete these functions, apply this patch, and we get another problem. However, we're making progress because the U-boot environment actually validated correctly. And now we see a different problem. That is because we haven't actually flashed rootfs. We don't have a file system on here. And so the next thing is to bring in Linux, to bring in rootfs, make that part of the FWUP configuration, and hopefully get into a nerve system. So adding Linux, we'll want to first add the configuration that we saw in the Linux repository that we have in our notes. And at the same time, we'll bring in the SquashFS patch, which ends up adding some performance improvements on top of Linux in order to improve the performance of SquashFS just a slightly bit. And we have to add obviously the configuration into our nerves diff configuration. And this is pretty standard. It's just taking all the information that we've collected in our notes here, setting up the URL. We pinned it to the last commit in the branch that we found. We used the local def config that we copied over. And the last thing that is very important is we saw those device trees that we need to include. So we tell built-root, hey, these are the device trees that I want you to compile along with the Linux kernel. And there's a little bit more configurations that we're going to want to make because for the main partition, we use flash-friendly file system, F2FS, and that is used for our data partition. This is specifically designed for NAND flash storage, such as SSD and eMMC. And for most nerve systems, that is exactly what we use for our data partition. So unfortunately, the def config that we copied over did not, for the Linux kernel, did not have that configuration. We just have to add it in. So now that we have a fully built rootfs file, we can just add it into our FWUP file resource, also add it into how to actually write it, what offsets. I know I didn't get into that. That is not really Yocto specific. It's more nerves and built-root specific. But just the important thing is bringing in the rootfs, which is what we're going to need next to actually boot into the system. And there are a few last bits to add here for the configuration in order to properly boot into a nerve system. F2FS tools. This is not required. The system won't crash, but message of the day uses F2FS tools to display the disk consumption on your hardware, and NBTTY is used by Earl init. So now that we've defined or actually added the rootfs into our def config, we should get the happy hello nerves window after we flash and brought the entire system up to life. Now this path was the happy path. There is gotchas and issues that could come up during this entire process. There are ways to get around them. There are ways to troubleshoot. But the good thing is we have a reference system, that board support package from Compulab. If that was able to build and produce an embedded Linux distribution, we should be able to replicate it based on that exact configuration. So the key takeaway here is always start from a reference and build your nerve system from that reference. It could be Yocto, it could be another sort of building technology, but it's always easier and a better idea to start from a good known reference. Otherwise, you'll have a very long and hard time going through data sheets. That's all that I have today.
Awesome. Thank you, Abelino.